I don't know, I've just been spending most of my afternoon going to sessions and learning about data stuff, and definitely been very educational. I know a whole lot more about data science than I did when I entered this because I knew nothing before this.
Well, that's awesome. I'm glad you're here and that you've enjoyed it so far.
Yeah, definitely like going off of what Caleb said, I think like because I'm a freshman, I had a very minimal knowledge of everything. And so like there are so many things that like in theory, I guess you can kind of understand and wrap your mind around, but then like in practice kind of coding that and making it become an actual thing, excuse me, is like just watching that process and learning about all the semantics that go into it and all that stuff has been very interesting.
Yeah, and you found it early too as a freshman. I know I didn't start getting into data science until it was my junior year of college. So last year I'm a senior. And so I think events like this, I love that we put it together because there really isn't a whole ton of data science you can learn through classes at A&M. I feel like most of my data science learning has been outside of classes. So I love that y'all are here and you're able to kind of learn some of that with us. All right, well, I'm going to send you guys a collab link. I'll put it both in the chat here and I'll put it in the chat on Discord too, so whichever is easiest for y'all. But I'll go ahead and send it over. All right, so you should have access now to this collab. And this is a continuation of the class that Josiah just taught, the ML Part 1. If you weren't able to go to it, no worries. They're distinct enough that I'm not going to cover anything necessarily based off of what he said. So it's separate enough that you won't be lost. Yes, if you haven't seen it, you should also go watch it. It'll be posted pretty soon, actually, up on the website. I'll go ahead and start sharing my screen with you guys. Hey, John, can you let me screen share?
Yes.
Right, thank you. Okay, so in part 2 of machine learning, we're really going to be focusing on the applied section. I know the last time it was pretty theoretical, and this time we're actually going to get into some models, some more advanced models, and just kind of go over exactly what the thought process is behind those and do some implementation of it. We're also going to talk a little bit about, I don't know if logistics is the right word, but that's the word I'm thinking of when I think of kind of how to train, test, split, how to cross-validate, how to decide your decision boundaries. So more of kind of the nitty-gritty behind machine learning models as well. And so we'll go ahead and we'll start by defining some terms. So accuracy is just a term you want to keep in mind. It's pretty intuitive. It's a % of time you get predictions right. So it's just something to keep in the back of your head, as well as ground truth. So ground truth is the actual correct value. So that's just another term you also want to keep in mind as we go through the rest of this. We're going to start out by talking about classification. If you know anything about regression, between classification and regression, these are two of the core types of supervised learning. And so supervised learning is the type of learning where you have a data set with known outcomes. And so you try to train a model based on this data set to predict future values, but you know the outcomes. And so you can either have a classification type, which we're going to talk about today in detail, and that's when you are predicting a class. So in this example, if you have a student and you're predicting whether or not they're going to pass or fail, that's classification because you're trying to group them into a certain box. Versus regression, which if you learned about that before, that's more of you're actually predicting the number. And so with this example, instead of saying if a student was going to pass or fail a class, you would actually try to guess their percentage or their grade. And so that's kind of just a high-level overview of the difference between classification and regression. And there should be a video that we're going to start and it's about decision trees. So decision trees are a way that we can go about classifying. There are a lot of different types of classification algorithms. There's logistic regression, if you've heard of that. That's a pretty popular one. There's also decision trees, which leads into random forests, which we're going to talk about too. But so I'm going to go ahead and play this intro to decision tree video for you. Just a few minutes. We'll cut it off before it goes too far, but it gives a pretty good glimpse. I'm going to make sure I think I'm going to stop sharing for just a second to make sure I can share with good video or with good computer sound. Okay, so hopefully this should be pretty good for y'all to hear.
Here's a simple decision tree. If a person loves StatQuest theme songs, then that person is awesome. And if a person does not love StatQuest theme songs, then that person is slightly less than awesome. In general, a decision tree asks a question and then classifies the person based on the answer. It's no big deal. This decision tree is based on a yes-no question. But it is just as easy to build a tree from numeric data. If a person has a really high resting heart rate, then that person had better see a doctor. And if a person does not have a super high resting heart rate, then that person is doing okay. Here's one more simple decision tree. This decision tree is based on ranked data, where 1 is super hungry and 2 is moderately hungry. If a person is super hungry, they need to eat. And if a person is moderately hungry, they just need a snack. And if they are not hungry at all, then there's no need to eat. Note, the classification can be categories or numeric. In this case, we're using mouse weight to predict mouse size. Here's a more complicated decision tree. It combines numeric data with yes-no data. Notice that the cutoff for resting heart rate isn't always the same. In this case, it's 100 BPM on the left side and 120 BPM on the right side. And the order of questions on the left side, first about resting heart rate, then about eating donuts, doesn't have to be the same on the right side. On the right side, the question about donuts is asked first. Lastly, the final classifications can be repeated. For the most part, decision trees are pretty intuitive to work with. You start at the top and work your way down and down till you get to a point where you can't go any further, and that's how you classify a sample. Oh no, jargon alert! The very top of the tree is called the root node, or just the root. These are called internal nodes, or just nodes. Internal nodes have arrows pointing to them, and they have arrows pointing away from them. Lastly, these are called leaf nodes, or just leaves. Leaf nodes have arrows pointing to them, but there are no arrows pointing away from them. Now we are ready to talk about how to go from a raw table of data to a decision tree. In this example, we want to create a tree that uses chest pain, good blood circulation, and blocked artery status to predict whether or not a patient has heart disease. The first thing we want to know is whether chest pain, good blood circulation, or blocked arteries should be at the very top of our tree.
This is Mongolia, and we are Nada, the only company in the world who's...
All right.
We start by looking at how well chest pain alone predicts heart disease. Here's a little tree that only takes chest pain into account. The first patient does not have chest pain and does not have heart disease, and we keep track of that here. The second patient has chest pain and heart disease, and we keep track of that here. The third patient has chest pain but does not have heart disease. The fourth patient has chest pain and heart disease. Ultimately, we look at chest pain and heart disease for all 303 patients in this study. Now we do the exact same thing for good blood circulation. Lastly, we look at how blocked arteries separates the patients with and without heart disease. Since we don't know if this patient had blocked arteries or not, we'll skip it. However, there are alternatives that I'll discuss in a follow-up video. Remember, the goal is to decide whether chest pain, good blood circulation, or blocked arteries should be the first thing in our decision tree, aka the root node. So we looked at how well chest pain separated patients with and without heart disease. It did okay, but wasn't perfect. Most of the patients with heart disease ended up in this leaf node. And most of the patients without heart disease ended up in this leaf node. Then we looked at how well good blood circulation separated patients with and without heart disease. It wasn't perfect either. Lastly, we looked at how well blocked arteries separated patients with and without heart disease. Note, The total number of patients with heart disease is different for chest pain, good blood circulation, and blocked arteries, because some patients had measurements for chest pain, but not for blocked arteries, etc. Oh no, it's another one of those ghastly jargon alerts. Because none of the leaf nodes are 100% yes heart disease or 100% no heart disease, they are all considered impure. To determine which separation is best, we need a way to measure and compare impurity. There are a bunch of ways to measure impurity, but I'm just going to focus on a very popular one called Gini.
All right, so that was the video. Let me switch back over for just a second. The Zoom thing's in the way. There we go. All right. Okay, so in that video, it described decision trees, which compared to a linear regression model are really cool because they enable you to do classification, which linear regression doesn't really allow you to do, but it's also super interpretable, which a lot of the more advanced algorithms that deal with classification are not. So it's a good kind of in between. It lets you really understand what's going on and lets you do both regression and classification. And so in that video, it kind of walked you through exactly what a decision tree was. And you could kind of start to see how you could take a table and you could start to make decisions and classify things accordingly. And what they got to towards the end, when he was talking about the purity of a decision tree, that's something we're really going to focus on. So I'm flipping back over here just to see it. But right here, so when it goes through this decision tree and it gets to this node and it has things that it has sides on both yes and no, that means that it is impure. It did not predict with 100% accuracy because you saw things from both classes. But the goal is to get down to a point where you like make it as pure as you possibly can, because then you're more confident in your answer. And so the way that this measures it is with the Gini score, which is actually pretty intuitive. I'm going to see some point in time, I think, to kind of show you what they're doing here. But the impurity score is 1 minus the probability of a yes squared minus the probability of a no squared. And here, yes and no are just kind of the names of the classes. The classes aren't always yes and no, but it's just like 1 minus the probability of class A minus probability of class B. And so if you have perfect, if you're perfectly pure, then your score is going to be 0 versus the like worst possible score, like max impurity would be if you had a 50-50 split between your two classes, right? And so that actually maximizes impurity, and it does that. It's kind of like it's a quadratic function. So that would be like the maximal impurity is when it's 50-50. That's just something to keep in mind as we start talking about the effectiveness of decision trees. So this is what we're going for, is we want a node that is as pure as possible. And decision trees are worth talking about because they're not really used in production too often. Typically, things more like random forest or different extensions of decision trees are what you actually see being used. But just because of the interpretability and the way that things are based off of it, we're going to spend some time looking at it. So this iris data set, if you haven't seen it, it's used a lot in examples all throughout statistics. But what it is it has a data set with a couple of different features. So it has length, width, and then petal length and width, and then it has classes. And the 3 classes are the Setosa, versicolor, and virginica. And so what we're going to do is, based on those 4 numeric features, we're going to try to classify it into one of the different flower types. And this visualization is a really good one. It's pear plot and seaborn. I may need to try to scroll out for y'all so you can see it all in one. Okay. I don't know, that may be too small now. There we go. But so what this does, it's a symmetric graph. So we only need to look at the bottom half of it. And along the diagonal, so that's when the features are the same. That's actually a distribution plot by the species. And so you can see the species are color coded and the labels over here for you. But that's what's along the diagonal there. But we're really going to focus on the corners. So this really makes it easy to compare the classes under pairwise features. And so if we look at this one here, which is petal length versus petal width, what you're trying to figure out is how can you set off cutoff boundaries to where you can really split the classes with as much confidence as you can. And it looks like here, so this setosa, which is this blue one in the corner, it looks pretty distinguishable from the eye. You can tell that it's separate from the others. There's actually a couple different boundaries that I can kind of see. Does anyone want to jump in and say where they think the boundary would be? All right, so there's two ways you can look at it. So if you're looking at it by the petal length, where I think the boundary would be is kind of right after 2, right? So in between 2 and 3, if you were to draw a straight line here, you could say that any petal length underneath that could be classified as the setosa versus anything above it would not be. And similarly, you could look at it through the other dimension. So if you wanted to look at it through this petal width, bringing it over, it looks like it's between 0.5 and 1. You can see that if you were to cut a line right there, you could also use that feature to classify setosa versus the others. Now, if you look between this virginica and this versicolor, there really isn't a line that you can draw perfectly there because there is some intermingling of the data, so it's not completely separable. So that one doesn't look as clear to the eye, but this setosa, you can really see that you can separate it. And so if we wanted to fit a decision tree using these 4 features with our target as the species, we could do so. There's a feature or there's a package in sklearn, so it's tree. And there's this parameter called max depth, which I'll get back to you in a little bit. But similarly to any of the other sklearn models that you've seen so far, it has very similar syntax. So you would just instantiate your model by calling the decision tree classifier, and then you can fit the model on your X and Y. And then with this, you can actually plot it and you can start to see the decisions that it's making. And so a decision tree is always going to pick the feature first that it thinks it can be the best. So it's always going, it's like trying to pick the feature that it thinks it can use to separate it best. And so that's what this first line is in these boxes. So it's saying that it thinks if a petal width is less than or equal to 0.8, it thinks that's going to be a good separator. And so if we go back up here and we see where this petal width is less than or equal to 0.8, well, that's that line right here that I showed y'all just a minute ago. If you draw that line across, you can see how it really separates the blue from the other colors. So it separates one class from the other. And so that's what the decision tree picked up on. It thought that was the best line to start with. And the lines below this, so below the petal width, this would be if you didn't make any decision, what would your state be? And so to start out with, you have, let's see, 150 samples, because if we go back up to the description, it has 3 classes and each have 50 instances. So you're starting at 150. They're equally split across the 3 classes. And then this would be your Gini score. And then this class prediction here is really kind of arbitrary because they're evenly split. So there really isn't a clear class to pick. There's not an advantage. So yeah, that's how you would look at these boxes. The bottom 4 are the current state versus the top line is what the model is trying to do. So if we look at this decision it was trying to draw, so it was trying to figure out if petal width was less than or equal to 0.8, the yes would be on the left and the no would be on the right. So like we saw, when the petal width was less than or equal to 0.8, we really separated that class in the corner, which was the setosa class. And so in fact, when we draw that line and we come down here and we say, yes, petal width is less than or equal to 0.8, we actually get perfect purity on that setosa class. So it was a perfectly drawn line. Versus once we come on the other side, we are left with the other 2 classes. I'm going to scroll back just so you can kind of remember what we're talking about. So we've isolated now this blue section, and we have this orange and green that are kind of intermingled that we still need to separate. And so it tries to do that with petal width, and then it ends up going down here. And you can see how the Gini scores, we said when it's perfectly pure, it's a 0. And so it's getting closer to 0 as we continue to go. It's starting to split them better, but it doesn't ever get perfect on these 2 because they're so intermingled. We didn't find the decision boundary that split them. And so if you notice with this tree, it's really short, right? We didn't make a super deep tree, and that was because of the feature parameter we put in there. It was the max depth. And that's something that we really need, there's this like variance bias trade-off in machine learning that you might hear about a lot. But if you were to make the depth really, really large, you could have a giant tree and you may predict really accurately in that particular instance, but that could also be overfitting, which you want to avoid, because if you overfit something on your training data and then you get new testing data, you like the variance there. So like if you get a point that strays a little bit, you may not be able to predict it well at all. So this is something you don't want to overdo. You don't want to make the depth too large if you don't have to. And so that's why not only like we wanted to be able to visualize it, yes, so we cut the depth off, but you also don't want to just let the depth run real large either. So that was the first example. And then we're also going to look at this Titanic example, which is another pretty popular data set. So in this, it's actually data from real Titanic passengers, and you have several different columns. We need to do a little bit of data cleaning with this as well, because for machine learning algorithms, you really can't have textual data. So you need to somehow convert those into numbers. So we're going to have to do a little bit of cleaning before we can pass it into the model. But what we're trying to do, so I'll actually just show you some of the data cleaning first. So with sex, we have male and female, which we're going to binary encode. So I think here it's going to be, I believe it's male would be 1 and female would be 0. So we're going to go ahead and encode that. And then we're also going to one-hot encode for the class. So that is this right here. So first, second, third. And so one-hot encoding, if you're not familiar, what it does is for each of the possibilities in this column, it creates another attribute. And so now these are each their own column, and it's a binary indicator. So and for example, this first row right here had third class. And so it's going to be a 1 here because it was third class versus a 0s in the other. So that's something that it's a way that you can expand your feature space in order to have numbers instead of textual data. And so that's what we did to this data set first in order to be able to run stuff on it. And then once we have that all set, and this is a little bit more, it's just kind of filling in NaN values, doing a little bit more data cleaning. But basically what we end up with is this X of our features and our Y of our target name. And so what you're trying to do now is fit a decision tree classifier to go through this data and see whether or not, given certain columns, we can predict from it. So what we're trying to figure out is whether or not someone died or they survived on the Titanic given certain features. And so we fit our decision tree classifier just like we saw before. And the first thing to notice is what our state would be before we tried to make any decisions. So we had this 891 samples, and more died than not. So this was 549 that died and 342 that didn't. And so the class that it would just automatically assume if you didn't make any decisions, it would predict that someone died just based on like the fact that more people died than not. So this is kind of your base decision here. And now what the decision tree decided to say was, well, was the person male or female? And here it's a little weird to think about male and female in terms of like 0.5. That seems kind of like a weird decision boundary. But if you remember when we encoded it, male would actually be a 1 and female would be a 0. So if we go down this way, we're saying, is it a female? And notice that now, even just switching to female, the classes now, we're not going to predict that they will survive instead of died. And that's because on the Titanic, it was like women and children first, I believe. And so it kind of makes sense based on what we've heard before. And so even just that switch, we've now flipped a little bit. And you can see this reflected in the value as well. There were 81 that died versus 233 that survived. And then if you go over here to where it was male, you're still very heavily on the did not survive side. And so then the next layer is once you decided that it was a woman, you now want to figure out whether or not they were third class. And because of the way that this class variable was defined, so if you were to say yes here, that would mean that you aren't third class. So it could be either first or second class is the way that logic works. And so if you were a woman who was first or second class, your probability of survival in the Titanic was really high. And you can see that here. Versus if you were a woman and you were third class, you were predicted to have died. And then here would be male and then a youth. So like a male baby would be predicted to survive versus a male who was older than the age of 6.5 would be predicted to die. So I think this just really goes to show just how interpretable these decision trees really are. You can follow the logic really clearly and see exactly what the model was thinking at each stage and why it made the decision it did. And so between these two examples, I think they give a good overview of what decision trees are trying to do. There's also this little tool if you wanted to see, these are fun to do in Collab, but you could go through and click certain things. So if we wanted to see what a male, actually I probably would need to run some stuff before I demoed it for you. But if you want to play with it in your own Collab, you can mess with these parameters and you can scroll around and it'll update the probability of survival for you based on the decision tree model. So you can see how the tree made its decisions. And then something else that I mentioned, so decision trees can also be used for regression, which is really neat. So the above example, we were predicting whether or not someone survived. So that was classification, it was binary. Here, we're actually going to try to predict the fare, so the amount they paid for their ticket. And this will be a regression type of problem because it's not a class anymore, it's actually a certain value. But you can still use decision trees the exact same way. So like we talked about with this first box, if we look at the bottom of it, that's kind of what the state would be before you make a decision. So we have the 891 samples, and then the mean value of fare is actually 32.204, which is why that would be your prediction. So you would just predict the mean if nothing else. And the same way we kind of followed the tree on the above example, you can do that here. So you can go through the logic and it's just now calculating the mean based on whatever conditions it's in. So that's what it's going to predict instead of a class. So when it makes class predictions, it takes whichever class has the higher proportion. When it makes regression predictions, it takes the mean. And so the same logic applies to both situations, which makes this like decision trees really valuable. Okay. And so I talked a little bit about overfitting above, but test train split is one way that it's just really important in any type of machine learning model to make sure that we don't overfit. Because if you, I'll show you with these pictures. I think these pictures are actually really helpful. So if you look at this model on the left, you can see so that the dots are the model and this line is the like model we're trying to fit to it. Sorry, dots are the data, the line is the model. And here it looks like we're fitting a straight linear regression and it doesn't do so well. So that would be what we would call underfit. So you wouldn't expect it to be really accurate. Versus if we go all the way over here on the right, it looks like the line fits the data almost perfectly, but this is definitely a really high order polynomial function. And so it's what we would call overfit. And so if we think about this in terms of this bias variance trade-off, so bias is how close you are to the expected value. So if you come over here on the overfit side, any point you're going to pick, your bias is going to be really low because you're predicting accurately. So you're not going to really have a bias data set, but you're going to have a very high variance data set. And what this means is if you have this curve and say you add a new point and the point is, I assume y'all can see my cursor, let me know if you can't. But if the point is way away from the line, you're going to have to completely redo your model. Like the model will not fit it at all. And so that's why it's super high variance. Versus over here on the underfitted side, if you add another point, it's probably not going to mess with the placement of your model much at all because it wasn't real tight fit to begin with. But right here in the middle, this is kind of our sweet spot. We want to find a model that has just the right number of terms to be a good predictor, but something that's also really robust. And so we're going to use test train split to help us do this. So let's see. What test train split does is well, first of all, you can find this function from sklearn, and you just pass in your x and y. And what it'll do is it defaults to, I'm not sure what it defaults to, but you can set the percent that you want to become your training set and your testing set. And what that does is it'll reserve a portion of your data to be tested on. So you're not fitting the model to everything. That way you don't overfit, because you can like train it on part and then test it to make sure that it still works even on new data. You're not like putting all of it into the training pool. And so it's really useful. Yeah, it's really just as simple as calling train test split on your X and Y. This stratify Y parameter, what this does, and you don't always have to use it, but it can come in handy. But if you do this, it will try to make sure that it's dividing evenly among classes. So for example, here we can see that the test and training data have about the same percent survived. We fit it on the Titanic problem, I believe. So it tried to keep that about the same. That way it wouldn't mess with your model. You're expecting about the same percent in test and train, even though it would have different features. Your outcomes are like stratified to be the same. So that's test train split. And then this model, this graph down here shows you a little bit more about overfitting. And as you can just kind of see this curve. It has this curve to underfitting and overfitting. So as you keep increasing model complexity, you're going to get increasingly better on your training data because you're going to fit to it more perfectly as you keep going. So there's a sweet spot on the test data, however. You want to get just enough that you're getting important information, but if you go too far, you're going to overfit, and then your testing data, the accuracy on that is actually going to decrease. So you want to find this like minimal point if you can on the testing data. That would be your sweet spot for model complexity. And if you were to play with this a little bit, you could mess with it and parameters and just kind of see as you affect things, how does the training and testing score change? The next kind of thing I want to talk about is cross-validation, which is just an extension of test train split. So with test train split, you just take your whole data set and you split it once. You have training data and testing data, you have two parts. What cross-validation does is it extends this to do this multiple times. So in this example, it looks like, well, it's generalized to k-fold cross-validation, but say it kind of looks like we have 4. So let's just say this is 4, we have 4-fold cross-validation. What it would do is you would split up your data so that your test data was a different portion in each of the 4 iterations. So you can kind of see how in iteration 1, this would be your training, that would be your test, and you're flipping it on every iteration. That way you are really making sure that your model is as accurate as can be. So it's just doing test train split over different portions of the data. And the way you can do this, you can import cross-val score from sklearn, and then you just run the classifier just the same as before, and then do the cross-val score, and you get all of the different scores from setting aside different portions of the data. And so again, this just really helps to overfit to make sure that your model performs about the same on every iteration. And now we're going to take a look at random forests. So random forests are an extension of this decision tree concept that we've been talking about. It's a very up and coming algorithm. I use it on almost all of my data science projects, and it's just, it's my go-to. It's what I try first before anything. So it's called bagging, which stands for bootstrap aggregating. But what it does is, so if we think about the decision tree that we had, that starts with all of the data. Well, random forests are going to make lots of decision trees all at once. And they do this kind of randomly, hence the term random forest. So it's literally going to take the data, and some trees are going to have some columns, other trees are going to have different set of columns, they're going to have different rows. It literally just kind of subsets the data across these different trees. And then you would run a decision tree on each of those subsets. And then based on the decisions that each one makes, you take the majority of those, and that becomes your prediction. And so I'm going to kind of walk you through an example if that's a little bit hard to grasp. I know I've had to think about it before. But say that you were trying to pick a movie to watch and you wanted to get some input from your friends. And so you asked your friend over here, and she has only seen a couple of the movies you've seen, so not all of them. And they may only focus on the actors in the movie. Maybe that's what they care about as their feature to base their decision off of. And maybe your other friend has seen a different set of movies you've seen and they care more about the genre, and so on. So you can kind of see with that example, you like the trees are like your friends there. They've seen different things as you, they care about different features, but they're all going to give you a prediction on what movie you should see. And if you went and got advice from all of those friends, then you could then take the majority vote and say, well, most of them say to go see this movie. And that would be what your answer would be. And that's just what random forest does. It splits the data randomly and then takes the majority vote, and that becomes your prediction. And that's actually, it's really powerful because instead of just basing your decision off of one, you're basing your decision off of multiple trees. And if there's error, that also helps kind of hide error a little bit more, because if one tree goes wrong and the other trees go right, you're taking that majority vote. And so it enables a little bit more error within trees because you can kind of mask it as long as the majority is in the right.
Do all the trees have different parameters that they like decide off of?
Yeah, so if we think about like the Titanic data set, if we go, I don't know how far up here that is. Yeah, so let's say we split this into different trees. Maybe one tree only cared about whether it was male or female. And so like that was, if you think about it in terms of a table. So if you were literally taking random parts of your table, you could say tree 1 would have columns 1 and 2 and rows 1 and 2. And tree 2 could have columns 3 and 4 and rows 3 and 4. So you're literally taking random subsets, both in rows and columns. And that's how the trees are made. So it does care about different features. Does that answer your question?
Yes, thank you.
Yeah. Let's go back here.
And it also chooses random samples of data?
Yes, yeah. So
Okay.
it subsets on both, like the data and the columns.
All right.
Mm-hmm. Yeah. All right, so the next thing I wanted to hit on a little bit is feature importance. This is another way that we can really fine tune our model, because if there's any way that you can trim down your data at all, that's helpful. You don't want to include things you don't need. And the neat thing about sklearn, it's a really great package for anything related to machine learning. But a lot of the models, once you fit a classifier, they actually have this attribute called feature importances, so it's built in. So this is one of the ones I think would have just run off of the random forest classifier. So it's built in, the feature importances, and you can plot them and you can see how influential they were in making your decision, like how much they were based off of. And so in doing this, you can start to kind of, if you see one that's really not important, maybe you want to build the model without that next time and see if you can get it even better, like not even put that variable in the mix to be considered, just in case it skewed things wrong. So yeah, that's just a way that you can really make everything easier. You can also, there's some good points in these bullets as well. If you know that you don't need certain variables, that also means if you're collecting more data, you don't even need to worry about it. You can ignore it. You don't have to take the time to find that data. And it saves computation time too if you're not having to mess with features. That's one way, it's just built in, you can kind of see it. And then there's also hyperparameter tuning. Many of these complex models have parameters that you need to kind of find the best value for in order to produce the most appropriate model. And there is this randomized search CV that you can import from sklearn. And the CV stands for cross-validation. So it's kind of applying that same principle of searching throughout the data set. And what you could do, so in a random forest, for example, here are some of the parameters that we have. So we have number of estimators, your max depth, your min samples, bootstrap. We didn't go over exactly what all those parameters mean, but they're here in the comments too if you're curious. But what you could do is if you wanted to try to figure out what the best combination of those parameters are, is you can set some ones that you're curious and investigating. And then if you put it into this random grid, it takes this format. So you would say the name of the parameter, and then you would give it your ones you're looking through. You can put that through a randomized search CV. And what it'll do is it'll find the best parameters. It'll take every combination of those parameters you give. So it could take a little bit of time to do a grid search, especially if you have lots of combinations of parameters that you're needing to test through. But it pops out the best parameters, and then you can use that in your model, and you know that you're doing the absolute best you can with the data you have. And I think there's something in the chat, so I'm going to check. Oh. Okay. Yeah, so that is what hyperparameter tuning is, just an overview. It lets you really just make sure that the model is as good as can be, and it's based off of cross-validation. All right. So then the next thing that we can talk about are decision boundaries. So these help you visualize classification. And so let's see, I believe most of this is already run, which is good. But here, this looks like a logistic regression model. I'm not sure if y'all are familiar with logistic regression or not, but you can see at the bottom left side, you have one class, or what appears to be one class, and at the top you have another. And logistic regression is an extension on linear regression. You can actually use the linear regression equation, but then flip it to be predicting log odds instead of your actual value. I don't have the equation here to show you, but it's a similar concept. But it produces the sinusoidal function. And what it does is you can try to find this boundary of where, and typically your decision is at a 0.5 probability. That's normally when you would switch over and classify something different. But here, this 0.5 probability intersects right around 5. So that would be your decision boundary in terms of predicting whether or not something was a class 0 or a class 1. So if we look here and it's at the 5-ish months, if it's under 5, we're going to go ahead and assume it's 0, because that's what this would do. It's like rounding almost. You're under the 0.5, so you're just kind of round it all down to this class 0, versus over here, you're now in the 1 area. So this is just a way that you can kind of see how something would classify it. These are just other visualizations that point out how decision boundaries work as well. So this is a different view of the exact same data. So you can see that this green line is the same. And there's a couple samples on either side that would be classified incorrectly if we use this decision boundary. You don't quite get them all because it wasn't perfectly separable. And you can tell that here because I'm zooming in because it's small. You can see there's some crossover right here. It's just a different view as well. And then these are a couple things about decision trees as well that I won't go too deep into, but just more visualizations on how your decisions actually appear to sort the data. I think we're gonna skip over that. Okay, so then the next thing I wanted to talk about is a little bit of scores beyond accuracy. So accuracy is the one we talked about at the very beginning. It's just how often your predictions are right. That's accuracy. It's commonly used, but there are cases in which you wouldn't actually want to use accuracy to evaluate a model. So for example, if your classes are really, really imbalanced, that's a situation that you don't want to use accuracy. And there are some alternatives to that. You could do a weighted accuracy. You can look at like false positives, false negatives, true positives, which then those in turn become these metrics called precision and recall in F1, which we'll talk about. So one thing we would want to do is look at if you have unbalanced classes. So this is if instead of having like a 50-50 split naturally, say you have well, this is an example here, but on survived and didn't. So you had, let's see, Yeah, so you had 549 that didn't survive the Titanic, and you had 342 people that did. So those are imbalanced classes. You're not at a 50-50 split. And so you don't want to use just simple accuracy. You want to use a weighted accuracy. And in order to do this, you need to kind of figure out the proportion of times it appears and then use that kind of as your counterweight. And this just will help you get a better grasp instead of just doing a straight accuracy. And then there's also this instance of a false, true, negative, and positive. So if you've seen a, I remember the word for it, like a classification matrix, it talks about, or I think it's a confusion matrix, I'm pretty sure. It talks about how your classification actually ended up being. So a true positive is if you predicted true and it actually was true. So that would be a true positive. A true negative would be when you predicted negative and it actually was negative. So those are the cases where your model like classified stuff correctly, either correctly positive or correctly negative. Those are true positives and negatives. And then you have false positives, which would be if your classification predicted positive and it wasn't positive, and false negatives, which is if you predict negative and it wasn't. So these are the cases in which your model errs, is if you get a false positive or a false negative. That's just a way to, these are functions that you can use that to calculate if you needed to. And we can see this confusion matrix here. So this resembles that logistic regression curve we saw a little bit ago. This green line would be your decision boundary here. It's where it intersects the 0.5 mark. And these are your two classes. So this class in the bottom left corner, in this case, you would like, there are none that are on the opposite side of the decision boundary. So you know that all of these are going to be correctly classified. And typically you would say your 1 class is your positive class and your 0 class is your negative class. And so because these are all on the right side and they're all zeros, those are going to be true negatives. And there's no false negatives, or sorry, there's no false positives here because none of this data that was actually a 0 was on the opposite side of the decision boundary. So these are all classified correctly. But if you look at the top, that's where things get a little bit different. So your true positives are these ones on the corner, the far right, because they were past the decision boundary on the right side of the decision boundary and classified correctly. These ones on the left, on the other hand, are false, and that's because they were on the opposite side of the decision boundary. So you can see this class on the top you had some error with versus this class on the bottom you didn't. And this shows up in the confusion matrix, which is what I was talking about. It's just a matrix of one dimension is of the true. So was it truly positive or negative? And then the other dimension is your prediction. Did you predict positive or negative? And so here you can see that when it wasn't fake news, that was predicted very strongly correctly, right? So it knew when something wasn't fake. And that's this whole section down here at the bottom that we said we predicted with almost like with perfect accuracy. Versus the ones that were fake news, those were harder for us to see. And you can see here, it didn't quite do as well. It wasn't as sure in its decision. And then here are a couple of different measures that we can actually use as replacement scores. So you don't typically use like false positives, true negatives, all that as your score, but you put those calculations into other scores. And those are called precision, recall, and F1. So precision is the probability that you predicted positive, or sorry, the probability that it's actually positive given you predicted positive. So if we come up here and we want to see this in terms of the confusion matrix, so the probability that you predicted that it was actually positive given you predicted positive. So predicted positive would be right here, this guess fake news. And the probability that was actually positive is this one. So this is what your precision score would be here, is looking at that box. And then recall is the probability that you predicted positive given it was actually positive. So predicted positive given actually positive. So that's the opposite. So you would look over here, you would now take this 15 over the sum of these two things for recall, versus precision would be 15 over the sum of these two things. So that's the difference in those two. And then F1 is the score that we typically use to compare, and it's a harmonic mean of those two things. And so here's the equations for these. So the recall and precision just go through that logic that we had talked about. And F1 takes precision and recall, and it returns 2 times. It's the numerator is the product of precision and recall versus, and then the denominator is the sum of the two. And in this graph, if you wanted to mess with your parameters W and B, so if you think back to linear regression, you have W, which is like your coefficients, versus B, which is your intercept. So I had mentioned with logistic regression, it's very similar to fitting a logistic regression, except you're not predicting a number anymore, you're predicting log odds. That's the difference. But you still have these parameters W and B that you're trying to fit perfectly. And so if you wanted to kind of mess with this on your own and see how changing those parameters would affect this, you can try to get that sweet spot where you're going to have a better F1 score. So you want all of these things that were predicted false. You want to try to see if you can get more of those true. So you may need to scooch it over a little bit more, and that could be better. You could get a better score. All right, and then we have just a few more things that I wanted to cover in this lesson. So we started out with decision trees, which are really interpretable, and they take all of your data and one by one, they'll start with a column that they think is able to separate things. And then in the next layer, they'll decide on another boundary. So that's what decision trees do. And then we went to random forests, which are then groups of different decision trees that you pick the maximum or the most common prediction off of. And then there are some extensions even beyond random forests called boosting, which I, to be honest, don't know a ton about. I know these very at high level. But one of them that's really popular nowadays is XGBoost. It's gradient boosting. Yeah, those are 2 very common ones. And so with random forest, it's completely random. It subsets things, just asynchronously without really thinking about it. It takes different parts of the data and it runs the decision tree, and then it gives you an answer. Well, with XGBoosting, it actually thinks about it a little more. It doesn't just completely randomize it. If you split the data and you notice that one tree predicted really wrongly, its purity was really bad, then that would be something you would want to correct in the future. And so it's kind of learning as you're going. And so instead of just completely randomly splitting it at every level, you're going to start correcting for those errors. And so because of that, XGBoosting is an extension of random forest. It can do better in certain situations because you're ameliorating where it's bad. So it's random forest with a little more thought into how you're actually splitting the classes and the data. And then let's see, we still have a little bit of time. So first of all, I'll open it up for Q&A, and then if we have time at the end, I can also go through any questions y'all have about challenges. I think there's some application from this class into some of our Team Datathon challenges. So if y'all had questions about that, we can talk through those too. But if y'all have any questions, I'd be happy to take some. All right. Well, thank you all so much for coming and listening. I can actually, if you wouldn't mind, we're doing workshop feedback, and we'd love to know what you thought about the class and the curriculum. So if you're able to fill it out, it's 2 questions. So I can send that to you in the chat. All right, so Sarah, if you wouldn't mind taking just a minute to fill it out, that would be awesome. All right, well, if y'all don't have any questions, are y'all wanting to see a little bit more on challenges? Would you like me to walk you through any of the demos? Okay, it's all good. Thanks again for coming, everybody. I really appreciate it. I hope y'all are enjoying Dayathon so far, and have a good rest of your night.
Thank you. You have a good night too.
Thanks, guys.